Hi, welcome to this presentation. My name is Loek Cleophas, and together with the colleagues on this slide, I work in the Software Engineering Technology Research Cluster at Eindhoven University of Technology. Our mission as a research cluster is to develop methods and techniques for engineering high-quality software systems and to deal with the complexity typically involved in such high-tech, high-quality software systems. Our focus is on the use of models and model-driven engineering. So one topic that has gained a lot of attention recently is that of digital twins and digital engineering. The idea is to have a virtual counterpart to a physical entity or system and have that virtual entity be fed with data from the real system, sensor data, use it to do all kinds of analysis, for example, for what-if scenarios, prediction, predictive maintenance, and use the results of such analysis to then influence the physical system with the idea to optimize its behavior or productivity. And the overall idea is that digital twins and digital engineering are used to improve engineering and sustainability of engineering, high-tech systems and production systems. Like in model-driven engineering in general, models there are crucial, but again heterogeneous, so they come from different disciplines: software engineering, electrical engineering, mechanical engineering, and hence they are also interdependent. If I make a change in a mechanical engineering model, that might affect certain parts of the electrical engineering model as well, and certain parts of the software model as well. And because of the plethora of features and customizability in the current day, these models are also variant rich. So it's a complex ecosystem of models in play there. And in this ecosystem, we look at model-based and model-driven engineering of such digital twins, in particular of the virtual entities that are core to making a digital twin. So we want to look at questions like, how do we engineer these DTs? How do we manage the models that are used in them? In a setting with digital twins, probably evolution is easier and more frequent than in a setting without digital twins, because you can do so much on the virtual side before making changes to the actual physical system. But the models need to be kept consistent under such evolution. Also, at runtime, these models need to play well together. So they need to be orchestrated so that their combined behavior is the expected behavior of the virtual entity, mimicking the physical entity or system with respect to a specific purpose. There are other questions to be asked here as well. And I don't claim that we have answers to these questions, but as a starting point, we started looking at some case studies of digital twins or digital twins in progress, and what could be done there from a perspective of model-driven engineering and using models, and what are the issues that come to the fore there. And in this talk, I'll briefly go over one case study in particular, namely one for soccer robots, and I'll briefly skim on a beer brewing digital twin and an autonomous truck driving digital twin as well. So let's start with this 5D model of digital twins at a conceptual level. This is a model due to Tao et al. You see the reference on the slide here. And it considers digital twins to be made up of 5 components. One is the physical entity or actual system. The other is the virtual entity, which mimics the physical entity or system. Then there's the data being produced and processed by either physical entity, virtual entity, or both. And there are services on top of all of this. Services relating to the physical system, but also services related to the virtual entity, and therefore services related to this whole digital twin setup. And as a fifth element, we have the connections between these various elements. Now what we want to do is develop such virtual entities based on models. And these are heterogeneous, typically expressed using different tools and DSLs. So we have different disciplines contributing models, and they each have their own preferred tools. Might be commercial tools, might also be open source like SysML, or domain-specific languages developed in-house. For the physical entity, typically a high-tech system nowadays is also developed using models. Same models. So this begs the question of whether we can reuse some of these models. So for constructing the virtual entity that is part of the digital twins, can we reuse artifacts that already exist from the physical entity to more efficiently construct a virtual counterpart? And what is the effect on development and development time of a digital twin of such reuse? So our use case is that of turtle soccer robots. You see them depicted on the right here. So these are soccer robots that are based on a turtle robot platform with Omni wheels. And at TUE, the Tech United team has been developing such robots for over 12 years. They've been very successful in this, being world champion in 6 of those years. And the idea is that a team of 5 such robots and a 6th goalie robot can autonomously play soccer in teams on a small soccer field indoors against another robot team. So we've seen the 5D model of digital twins of Tau et al. Before. Here it's depicted slightly differently, but it's still got the physical entity, virtual entity, data, services, and the connections, the communication layer between them. And what we did was we mapped the available artifacts that were there from the physical entity, the physical robots, and the software and communication channels associated with it, to see how these mapped to the elements of the 5D model and what we could reuse. So looking at the physical entity, the actual robots were already there, well developed, mature, so we can easily map those to the physical entity dimension. However, Gijs, the master student doing this assignment, worked during the pandemic lockdowns, and access to the robots was severely limited because of this. Luckily, as a backup physical entity, there was also a simulator of the behavior of these physical robots that was actually used by the Tech United team to test their control software and their game strategy. And this simulator uses a very similar communication protocol to the physical robots. So for the purpose of Gijs's master's project, he mostly used the simulator as if it were the physical entity, the set of physical robots. But the digital twin that he developed is flexible in that it can actually use the actual physical robots and the data coming from the actual sensors instead of this simulator. From a high level of view, this is how the software system of the existing robots looked like. First, they had 4 models for motion, vision, the strategy of how to play the game, as well as a world model created by the robots for understanding the surrounding environment. We already talked about the simulator and the physical entity. The TRC in here is the Turtle remote control, which is used for controlling and monitoring the robots. I'll say a bit more about that in a moment. And the RTDB, the real-time database, is basically an abstract communication layer that I'll also talk a bit about. Okay, then with respect to the services, we looked at this Turtle remote control, which is a tool and graphical user interface to control the robots and start the game. It basically acts as a referee of a real soccer game would. But it can also be used as a monitoring system. It shows, for example, battery level, temperature of the robot, and several other pieces of information. So basically we concluded that we could use this remote control, TRC, as a basic set of services for the digital twin. Then let's look at the data and connections dimension. So the parts of the existing Turtle system were already quite well connected via this RTDB communication layer that I mentioned. It's basically a high-speed in-memory database which uses a producer-consumer model for communication. And it allows communication between all of the entities that need to communicate. We also looked at the data being exchanged via this RTDB. The screenshot here on the right shows a subset of that data. Yeah, basically that data turned out to be of high enough fidelity, both in what was in the data and how often it was updated. So we needed hardly any modification there to use this as the data for the digital twin as well. And then the virtual representation. We wanted a 3D a model of the robots to serve as a counterpart to the physical entities and better than the 2D depiction in the simulator that you saw before. There was an existing old CAD model from the design phase of the robots. It wasn't entirely up to date. It had far too many triangular faces to allow real-time rendering of 5 or 6 of such robots in a 3D environment. So Gijs actually managed to simplify and update this model to look far more realistically, have an actual kicker lag with realistic kinematics, while reducing the number of triangular faces to render by a factor of 50. So it was possible to render these real time. All of that, we managed to create a resulting 3D environment with 3D models of the robot moving around and operating realistically based on data coming from either the simulator that I mentioned or the actual physical robots. So these are basically interchangeable. And well, you can see information about the robots, and also as an additional service, we added a heat map just to see whether something like that was possible. So we took a system that looks like this and extended it to look like this. We developed a virtual entity with the 3D turtle robot models, a virtual ball, and both of these being updated as part of a 3D environment rendered in Unity, which in turn received data from the actual system, from the physical entity or the simulator. And for technical reasons, this was done via a communication plugin. Important to notice is that this is a one-way data stream from the actual system to the communication plugin and hence the virtual entity, which means that this is not yet a digital twin. We cannot use analysis on the virtual side to then automatically influence the physical entity. So that is a next step, developing this into a digital twin. But summarizing a bit, how about artifact reuse? Well, we were able to reuse quite a bit from the existing environment. the simulator and/or physical robots, the turtle remote control as a basic set of services, as well as the data being produced by the actual system. We also developed several components and integrated them with this existing system, the communication plugin, a 3D turtle model that was more realistic in terms of looks and behavior, as well as the connectivity from physical entity to virtual entity. So we showed that in this particular case study, it was indeed possible to reuse these existing artifacts in developing a digital twin or digital. So how did the availability of all the existing artifacts affect the development of the digital shadow or digital twin? Well, it definitely helped. Some time had to be spent on additional development, for example, updating the CAD models. And some time was spent on figuring out what the existing artifacts were, how they were connected. Basically, the architectural picture in the documentation wasn't always up to par, but still we are very sure that the ability to reuse many of the artifacts saved significant time in this particular case. Of course, these savings will be project specific. We can't say that this will in general be the case in such a setting where artifacts from development of a physical entity are already available. But our recommendation for now would be that one should plan for evaluating existing artifacts with an eye on reuse, and also with an eye on what will be involved to adapt the artifacts to suit the purpose. Think back of the 3D model. And we realized that we benefited in this case study a lot from the fact that these artifacts and models and software for the existing system were quite mature. This was 12 years in the making, so there was a lot of domain knowledge encoded in these existing artifacts, which made it easier to reuse. We have an ongoing master's assignment looking at predictive maintenance of the omni wheels of these turtle soccer robots. Please ask in the Q&A if you want me to say a bit more about that. Quickly, a glimpse on two other. So this autonomous truck case study related to a scaled down logistics warehouse distribution center we have at TUE in a research lab with scaled down trucks that autonomously drive and dock backwards at a docking station of this warehouse. That's the goal. There is a dashboard to visualize and control the actual physical entity, and there already was a virtual entity based on models, a 3D model in Unity for the visualization and dynamics of the truck, Simulink model, a monolithic one for path selection and control, as well as using IBM Rhapsody for requirements, overall structure and logical behavior. The Simulink model was quite monolithic, and we wanted to see, A, can we modularize this, and B, one of the reasons for modularizing is also that we want to enable using different tools for different purposes, depending on the domain. So what David actually did is he modified the virtual entity. He decomposed the Simulink model, and he used a framework called Ptolemy 2, which is for experimenting with cyber-physical systems. It's actor-oriented, and it has support for directors that orchestrate the actors. David chose this framework because it's open source, so he could extend it if issues turned up. It was well documented, and it allowed reusing modular artifacts expressed in different tools and connecting them together appropriately. And after some initial kinks in the cable, David in fact managed to use Ptolemy 2 to integrate these decomposed models in such a way that the behavior of the actual virtual entity was the same as previously seen. Then a beer brewing digital twin, and I don't have enough time to say a lot about that, I see. Basically, ask me about this in the Q&A if you're interested. It's a very interesting example of a chemical production process where we have some in-house expertise, and we're using this to investigate how to deal with integration, orchestration, and proper digital twin development in such a chemical process setting. And as a side effect, we're getting some nice beers to sample out of that. Thank you for your attention. I look forward to the live Q&A after this, or if you're interested, you're also very welcome to contact me using any of the means indicated on this slide.